Hi, so my name's Nick. I have been doing stuff with RTMP one way or another for about the last 6 years or something. Not by choice, it's just accidentally been what I ended up good at and then not so good at and then fighting with. And yeah, I've worked at a few places, most recently Twitch, which is a heavy user of RTMP. And I figured I'd give you a talk kind of similar to a talk I gave at Demuxed, if anyone was there, around what WebRTC was. This is kind of a follow-up sidekick of like, what is RTMP? So tonight I'm going to go through, so why do we care about RTMP? Isn't it an ancient history protocol? I'm going to give you a brief history of RTMP and some of the fun stuff that's happened around it. I'm going to give you a sort of a high-level protocol overview and then dive in and look through some actual docs around RTMP and sort of chat about what the protocol stream looks like. And then have a brief discussion around the future of RTMP and specifically some of the weaknesses of RTMP that are really sort of showing RTMP's age. So starting off, why do we care about RTMP? It was this thing that Flash used. It was like Macromedia created it back in the day. It's kind of done. Flash is dead, right? Well, not so fast, because, well, Facebook still uses RTMP. Twitch still uses RTMP. YouTube still uses RTMP. Twitter with Periscope still uses RTMP. Pretty much every large live video company out there uses RTMP for ingesting video. We've kind of moved on from RTMP on a consuming video side, but as far as pushing video out, it's pretty much the de facto standard. And it's just pretty much an accident that it ended up being here. The very brief history, and I'm not a massive fan of RTMP, in case you hadn't gotten that by now. I have written too much code that had too many bugs with RTMP to like it. So yeah, anyhow, it was created by Macromedia, acquired by Adobe, as basically powering video for Flash. You would connect an RTMP stream to a Flash media server, and it had a few different options. You could like play and pause and seek using this custom protocol. And they basically created it as an alternative to more complex protocols like RTP that were around at the time. RTP, as you hopefully know, is sort of the backbone of things like WebRTC. It's a really old protocol that was sort of heavily used by real-time communications use cases like voice calling. It has a lot of features like being tunneled over UDP that make it great for voice calling, but it also has a lot of features like originally requiring multiple ports to work that made it really, really complicated to set up and use. It also didn't have much flexibility. One of the other things that RTMP has is a sort of complicated remote procedure call mechanism built in alongside some shared object stuff, which is kind of all died away now, but back in the day it was what allowed you to do sort of complex client-server interactions using Flash. So it also has a bit of a contentious history, unfortunately. For a long time, it wasn't an open protocol. People started reverse engineering it. Groups like Red5, which is a open source Flash media server replacement, started in like 2005, 2006, making commits of like creating a new open alternative to Flash media server. Folks like Wowzer. Wowzer was actually created by people who bailed on Adobe after Macromedia was acquired and started their own company to create a competitor to Flash media server. And they, of course, kind of knew what RTMP was. They had a bit of a head start there. And their initial version, I think, was released in 2007. Tools like RTMP dump, which were pretty much just created so that people could rip videos that were being hosted on YouTube, were released around like 2008. And then time passed. Eventually, everybody reverse engineered RTMP. Everybody kind of figured out what was happening with Flash, what was happening with Flash media server, how to publish, how to consume. And Adobe eventually relented and released the RTMP spec in 2012. but it wasn't quite open. So they released a specification, but to benefit customers who want to protect their content, yeah, they didn't actually give you enough information to build a complete RTMP client, because they still really were selling the you can protect your content. Even though RTMP dump had figured it out by then, they were still selling it as kind of a proto-DRM. Even though the media wasn't technically encrypted or protected in any way, they were still selling it as if you could protect a flash media server. You couldn't. I'll get more into that later. But yeah, you basically got a kind of this license to build RTMP as long as you pinky sweared never to use it to save a live video or save a video. You could play a video, that was okay. You could publish a video, that was okay. But intercepting and like DDRMing was not okay. Basically, here's a spec that explains how to do RTMP, but H.264 ain't gonna work, this is me paraphrasing it, unless you know the secret handshake. We'll get more on that later, but there literally is a secret handshake. There's a handshake in the spec that says, just throw some random data in here, and we'll send you some random data back, and that's the handshake. And what they were actually doing is RSA signing that random data with a key in the Flash player, and if the Flash player got a correctly signed message back, it would decode and play H.264 content. But for the longest time, it was such a pain trying to get H.264 to actually decode in Flash over RTMP if you weren't using Flash Media Server. So like stuff like this is kind of why everyone kind of hates RTMP still, if anyone's ever like dealt with it. And they even sued Wowza. Basically, they decided that they had some patents, they created a lawsuit, and of course, in the meantime of this lawsuit, Flash died, and they kind of gave up on it because nobody cared anymore. So what is RTMP? So at a high level, it's a TCP-based protocol. Remember when I said it's like easier than things like RTP? That's because you basically just open a TCP connection once, and you can then, over that single connection, multiplex all the messages you need to do stuff with video. It's a bidirectional protocol. Adobe was doing things like building video chat services on top of RTMP, so you could both send and receive video over an RTMP stream, and in fact you could send and receive multiple streams if you wanted to have like a web conference over something like RTMP that is technically supported all over this single connection. So that was really important in terms of helping its adoption. That and Flash, this was the way to play video in a web browser. So it kind of got a huge install base because of that. So the way it kind of works is you have a stream that encompasses some sort of logical streams of video, audio, and maybe some metadata, all with a common timestamp. Those streams are demultiplexed into video, audio, and sort of message streams. Each of those individual audio or video stream is like a bad word to use here, are broken up into packets. So you'd have an AAC packet or an H.264 NALU that would be turned into a message. And then individual messages get broken up into chunks of a configurable size, which are then all multiplexed over a single TCP connection. So what does that mean? How is that different? Well, usually when you have a file on disk that's a video with some audio and metadata, you will have a video chunk followed by maybe an audio chunk. An video packet followed by an audio packet, maybe multiple audios between each video, but they're all sort of contiguous on disk. The video starts, it ends, and that's a frame. But actually, RTMP over the wire breaks that down further, so you can be sending part of a video frame and then send part of an audio frame, and then send a little bit of metadata, and then send something else. So the reason they were doing things like this is because it was multiplexed and because it was reused for things like RPC, they wanted, while you were sending a big chunk of video, they wanted to still be able to send other messages over that single TCP connection while that big video frame was sending. You can imagine that a keyframe could take 100 milliseconds or more to transfer, and during that time they wanted to still remain responsive and have other messages go over the wire. So hence that breaking up into smaller chunks that were then all multiplexed over this single TCP stream. So let's dive into that a little further. So I already said there's a handshake. It basically serves no purpose. It's just in there. It doesn't send any useful data whatsoever. It doesn't say, like, this is who I am, this is my capabilities. No, all that happens later. Maybe it's for rate control estimation? No, it's a lie. They had a secret handshake that just sent some random data and gave Flash and a Flash media server a chance to sign it and send it back. And that would then unlock the full capabilities of Flash. That was it. That was their super secret, don't tell anyone, or you can't use this spec. I'm hoping I'm not breaking, I don't think I'm breaking anything because I'm not implementing the spec right now. I hope nobody's gonna like rat me out. But we're not even going to go into the handshake because it's useless. You just like send some bytes, get some bytes back, great. But the chunk streams are really interesting, and they're so complicated. So as I said, these chunk streams are transporting messages, and messages can be like a video frame. So we have this high-level concept of a video frame, and low levels, chunks of that frame. So there are, over the wire, what that turns into is a single byte that tells you what the format of this chunk is and what the chunk stream ID is. And then, just to make it even harder, they put this all in one byte, so 2 bits are the format, there's 4 different formats, and the rest are the chunk stream ID. But in case you needed way more chunk streams, you could just put a 0 in there, and there would be like an extra full byte for you to use, minus 64, because you could fit 64 in that. Yeah, okay. And then if you maybe needed 2 bytes, so you wanted like tons of streams, you could do that. It's so complicated already. This is one of like the biggest problems with RTMP, is like, you can kind of see, okay, maybe I want thousands of logical chunk streams over a connection, but then you're just like, but I just want to publish some video. Like why do I have to have a varying? So you have to read the first byte, and then you can determine whether or not you need to read 2 more bytes or 1 byte to do it. And they didn't even stay consistent. Like, if you look at the chunk basic header 2 and chunk basic header 3, in 2, they're minusing 64 from your chunk stream ID. And in header 3, rather than minusing like 255, because you could have fit this one, yeah, they're just like, well, you should use the smallest representation, but you don't have to. It's just like, oh, come on. Okay, so then there are these 4 different chunk types. We've read the header, and now we know which kind of chunk we have. The first chunk has a timestamp, a message length, which is not the length of the chunk. We'll get to that later, but like, it's the message length, a message stream ID, and a message type ID. So, sorry, message type, message stream. Okay, then there was a type 1, which just had a timestamp delta, and a message length, a message type ID, and no stream ID. And then there was a type 2, which just had the delta, and then there was a type 3, which basically says everything is implicit. Okay, so wait, what? Why do they have these different types? They're all like just sending me, I could just use type 0 for everything. Well, yes, you actually could do that. You could use type 0, the full message for everything. But what they were trying to do is be clever and make people cry themselves to sleep when they were trying to reverse engineer this by compressing headers. So if you had a type 0, you'd put the full sort of message header in there. If you had a type 1, the message stream is implicit, and rather than having an explicit timestamp, you have a timestamp delta. Then if you had a type 2, you'd only need the delta. So the message stream becomes implicit. The message length is implicit, the type is implicit, and the stream is implicit. And then type 3 is everything is implicit. Okay, so why? Why would you do this? Okay, let's imagine you're sending an audio stream, and the audio stream has a consistent size. Each sort of AAC compressed sample has exactly the same size. The timestamps are all consistent. They monotonically increase by the same amount each time. You're using the same message stream ID, and you've got the same message type ID. What that would mean is you could send a type 0 full message, a type 1 a type 2 with a delta, and then from then on you can save all of the bytes in that header and just send type 3s, and it's all implicit. It's the same kind of audio sample that I sent you last time. It's kind of clever in that it makes your message smaller and reduces the overhead, but it's also really difficult to implement correctly. They also have extended timestamps. So I can only imagine the conversation that happened around this. Somebody was like, yeah, we got 3 byte timestamps. Is that okay? Yeah, that's fine. 3 byte timestamps. And it's like, yeah, we just wrap them around. Once you get up to the top, we'll just wrap around to 0. And if you get the stream, you'll just grab those timestamps. It'll work. You can just write the code, and you just be like, okay, well, if I went from a big number to a really little number, then we wrapped around, and my timestamp is now implicit. Okay, that's fine. And then somebody in the room was like, but I really want 4 byte timestamps, though. I'd really like that. So what they did was they decided to put like all 1s in those 3 bytes means there's an extended timestamp of 4 bytes, not 3, which just adds on to the end, destroying all of your header compression. And I have no idea why this exists, because even with those absolute timestamps of 4 bytes, you still need to wrap around once the number goes from really big to really small. And this actually happens. Elementals in the wild will do this. They will remember when you turn them on. They will keep a counter. They'll send you that counter. They'll send extended timestamps once they need to. And then once they get full, they'll wrap around in the extended timestamp back to 0. Just like catching that bug. Oh, man. And it only happens like once a month. Like, it's so bad. Like, that was a rough one. I got to level with you. Okay, cool. So if you're being astute, like, there's also chunkstream 2, which has a special meaning down in chunkstream land, which is its control messages. So it's always message stream 0. Message type IDs are reserved to tell you what this chunk means. The timestamp is ignored, which, okay, fine, like you couldn't, and anyhow. And the message size is like the same rules as the other ones, so you can kind of have like implicit, anyhow. Usually good implementations would always send the full header for the control messages. But the most important one was this chunk size message. So as I mentioned, the message size is different from the chunk size. So you get one of these chunk headers that's a type 0, or one that has an implicit size for the message. But your chunk size that you're using is implicit. It starts at a known value. I forget what the exact value is it starts at. But then you can send a message over RTMP to say, hey, I would like a different chunk size. And then if you get a message that's too big to fit in the payload of a single chunk of the current chunk size, you break it up over multiple chunks, and those extra chunks become type 3 chunks for header compression purposes, and then you have to accumulate all that data in a buffer for that chunk stream, and then once you get the final one, you'll kind of just have to track and know implicitly how big your final chunk is going to be, and oh man. So this is a fun one. So down at this chunk stream level, you kind of send this chunk size request, and then basically most implementations just set it really big so that we don't actually use any of that interleaving chunks features. We just kind of use them as messages. So this is kind of the low-level chunk streams. So to recap, chunk streams send messages broken up into parts. They can interleave these messages so that you can send these smaller chunks and interleave them all over the same wire, and they compress headers. They're really proud of this header compression, especially for audio multi-chunk messages. And it's actually really important. So in modern WebRTC implementations, RTP header compression is actually now, I think it's recommended, or it's being considered as being made required, where they're running into the same problem. If you are sending lots of small audio messages, you end up with this place where big headers eat up all of your, or a big chunk of your data that you could be using for audio instead. So things like this are kind of the things you run into when building a protocol, I guess. So now come with me on a journey to the message part. So the RTMP message format in the spec is given as this. but there's also a chunk stream message format given. So like, do you put this information after a chunk in the payload, and you put like message type, but the message type also matches the. So a lot of people were very disappointed when the RTMP spec actually came out, because what they're trying to tell you is, hey, look at this FLV format we have. It has a header, and then it has this notion of a tag, and FLV tags. FLV is like an audio-video data format that Adobe used heavily. Those have like a type and a data size and a timestamp. So if you were reading an FLV file, this is the format you would read it in. If you are reading an RTMP stream and getting a chunk stream, this is the format you can then push onto other things. So like FFmpeg, for example, when it's dealing with RTMP, if the stream you're reading in FFmpeg is an input, what FFmpeg will actually do is generate a new FLV header and then pass it on to its FLV handling code rather than actually do any real RTMP. So this is what they're kind of trying to say in the spec. Really what this is saying is, okay, you can send messages that have a type, that have a payload length, that have a timestamp, and that have a stream ID over the RTMP chunk streams. And they kind of tried to make a separation between, there's this low-level logical, we have chunk streams, and you can send these messages over chunk streams, and then a high-level RTMP style where you have messages, and this is not a format for an RTMP message. This is just some of the information contained within messages you can send over RTMP. And if you wanted to, if you built something that could take messages like this and send them over the chunk streams, that would make it really easy to send FLVs over RTMP. So that's kind of where this was coming from. So now we're getting into right into the weeds. So I mentioned earlier that RTMP is this sort of protocol that did a whole bunch of stuff. So one of the types of messages you can send is a command message of 20 or 17. That's the message type ID. So I put this text in here. It's like these messages are sent to perform some operations in AMF0 or AMF3 and do some stuff. It's like, okay, wait, what's AMF though? So this is coming from the AMF spec. The purpose of AMF is a compact binary format, but basically AMF is a binary format much like a binary JSON or like message pack or like Captain Proto or protobufs, where rather than having specific message types that you send over RTMP to do things, you would send an AMF representation of what you were trying to do, so it was very flexible to add in extra options. So if you actually look at how Flash and ActionScript worked, you would create a net connection, and you would net connection.connect to an RTMP URL. That would have a callback once you were connected, and then you could create a net stream on your net connection representing a stream, and then on the net stream you could call publish and publish some audio and video from Flash. You could also call things like netstream play, seek, pause, those kind of things. This was how the code that you were writing in Flash represented the connection. But how RTMP represents this is initially, once you have opened that TCP connection, once you have exchanged the stupid handshake, you could call something like a connect, and it would have things like a name of connect, a transaction ID of always one, because it's the first message you're sending, and then a command object that would include things like what app you were connecting to, the Flash version you were connecting from. Like, we still send this. If you open something like Wirecast and try to broadcast, we're sending a fake Flash version to the remote server as part of that initial setup of the connection. Not because we need to, Flash is gone, but it still kind of lives on in RTMP as we're using it. And all of this is encoded as an AMF object. In fact, you would even put in audio codecs and video codecs indicating what the Flash player that you had installed on your machine currently supported in terms of decode ability, decode and encode ability for your streams. Once this connect had been sent, you would then send another message, again AMF encoded, of create stream, saying I would now like to create a logical stream. And this would include things like a command name of create stream, and really what it was doing is it would put a stream ID in there saying, hey, I'm going to create a stream and I'm going to use this ID for it. Is that okay? Do I have permission? The response comes back, yes, you do have permission. And now you can use that stream ID that you put in to actually send audio, video, and data messages with that message ID once you called publish on the stream. Not quite there. So there were a few different publishing types, like live, record, or append. Nowadays, most people just use live, and what happens then is just implicit. But this is still the handshake. We're still sending over the wire, an AMF encoded connect, getting a response. OK, create stream. OK, publish. OK, there's often Flash Media Server required like other RPC calls on top of this, which are still included in like legacy applications. And then you could send this data, which was really just like FLV tags. If you look at this, you can sort of see there's a tag type, a data size, and a timestamp, like I mentioned. So bringing this all the way back to our chunk types, you can see that we have this timestamp, this message length, this message type, and this message stream, and it's from all the way up on high when we're calling these AMF remote procedure calls with like create stream, that we actually get this ID to then put all the way down in the chunk streams when we're publishing video. The silly thing is, you can practically just hard code all these values nowadays. You can just like say, okay, I'm going to have to send a connect, and then I'm going to get a response, whatever. And then there's a few other things in there you need to do. I'm just going to skip over for the sake of brevity. Then I'm going to send a create stream, and whatever, I don't care about the response. Then I'm going to send a publish, whatever, I don't care about the response. And then you can just send your data. So that brings us to the next question of like, maybe in the future, we might try and do something different. So the biggest problem we have right now is those initial connect messages have a hard-coded, hard-specified list of available audio codecs that you support as a Flash player. Things like Nelly Moser. I don't even know what Nelly Moser is. Like, I've never, ever known. Like, that's when back in 2010, when I was first doing this, I didn't know what Nelly Moser was. I think FFmpeg might support it, maybe. But you can see in this list, there's no like spare, there's no like negotiate me here option. They're all these numbers are taken. It's AAC or nothing. So if you want to use a modern audio codec like Opus, you basically just have to reuse one of these numbers, which is what people are doing now. Like you can connect to Wowzer and send it Opus if you reuse the correct number on this list. I'm not quite sure what it is. I haven't asked. I just kind of know that that exists. Similarly with video, they did exactly the same thing. Like RTP back in the mid-90s did this. They had the hard-coded list of codecs available. And then there was an RFC that said, that was a terrible idea. That didn't work at all. We have all these different audio codecs. We have all these different video codecs. Having a hard-coded list of them is never going to work. And the most annoying thing is there's already an RPC mechanism built into RTMP. We could just have if this had been built with a little bit more foresight, a message that says, yo, do you accept Opus? Do you accept VP9? And a response that says, yeah, sure, send it on this chunk stream ID. That's going to be fine. But no, instead we have a hard-coded list. Again, like onto VP6 looks like a great candidate for being replaced with VP9 in this stream. And that's what people are doing. But at the same time, it would be great if there was, I don't know, a standard around some of this stuff. There's also a bunch of stuff that happens around what we could do if we had a clean slate. Things like what WebRTC do, where the codecs and codec settings are actually entirely negotiable. And the server can sort of pick from your available list or even suggest some settings for you. It'd be great if that was completely flexible and future-proof. It would be great if this protocol supported more messages around things like dynamic bit rates and how you should be dropping frames when you can't keep up. And then there's a few sort of open questions right now around, should we switch to a UDP-based protocol? For all its kind of weirdness, one of the nice things about RTMP is that a lot of the live video community in terms of engineering is really used to it. We have open source implementations that work well. We have servers that know how to do it. TCP is really easy, whereas things like UDP, you have all these difficulties with rate control and how to build it in really well. And it would be really nice if we, in the future, had a simpler protocol without all of those little edge cases around exactly how to send timestamps, and without things like, do you want to send the extended timestamp or not? And then one of the things that's coming up is people considering switching away from RTMP entirely towards something like WebRTC, which has support for better codecs, which is secure by default, and which has a lot of these features. And I had a little slide here about TCP versus UDP. And essentially, that's the question. When you go into WebRTC, really there's one great implementation of WebRTC by Google right now, and not many others, whereas with RTMP, there are a whole bunch of different implementations that work well. There's ones built into FFmpeg, built into Nginx, you can grab Wowzer, like, it's just around, whereas WebRTC is a sort of order of magnitude harder to implement from scratch. Thanks. That was my talk this evening. Are there any questions? The biggest issue that WebRTC has right now is it doesn't have a data channel. So one of the things that RTMP has long had is a time-stamped, obviously WebRTC has WebRTC data channels. What it doesn't have is a data channel that is time-stamped alongside the audio and video. So in WebRTC, the RTP streams underneath are synced to the same clocks. And when you have things like captions on your stream, you really need those synced to the same clock. In WebRTC, you can like bundle those into the video, but if you just want more generic things, like you can put in your audio stream the little beep codes, but if you wanted to add in some metadata onto your stream, there isn't really a way to do that right now, and that's one of the biggest challenges around moving from RTMP to something like WebRTC. So it's mainly around getting to a good implementation of that server side. You really need, so one of the nice things about opening a single TCP connection and reusing it is you kind of ramp up, you do the sort of a gradual window size increase on TCP, and then you have the sort of full bandwidth of the TCP connection available to you. If you can do connection pooling and leave your connections to the server open, then doing something like HLS is relatively straightforward. The other challenge it has is there are a few messages in RTMP that give you a rough indication of what your bandwidth is right now. And rebuilding that on top of just a straight HTTP can be a challenge without that channel coming back around, this is what I think your bandwidth is right now, and you can use that information to sort of do a much better job of rate control when you need to drop frames because your connection can't handle your current settings. But yeah, people are using HLS or sort of fragmented MP4 uploads, although that's a little trickier, as well as RTMP. No, honestly, RTMP for client side is dead. Some people use it accidentally from now and again, but then very quickly moving to something like HLS for your distribution of content makes so much more sense than using RTMP, especially because the state machine of those chunk streams is so difficult to like keep and maintain. So yeah, no, absolutely you shouldn't be using RTMP for anything other than publishing right now. Like that's its last holdout. Because we haven't figured out anything better. Like what happens when your HTTP request gets disconnected halfway through? You reconnect and try again. But if you have limited bandwidth, and you've already encoded a chunk, a full chunk, you get into the situation where it's like, well, I don't have the bandwidth to upload this entire chunk again and stay real time, so you have to drop an entire chunk. Whereas if you have something like RTMP, where you're sort of live transcoding each frame and then trying to send it out straight away, when you get that disconnect, you just kind of drop everything on the floor, try and reconnect for a while, maybe in a loop. Honestly, yeah, there are so many better things we could be doing than RTMP publishing-wise that, yeah, there's no reason to be using it. Like, yeah, so there was like RTMPE, which it's kind of like that secret handshake. All I know about RTMPE is it sucks, don't use it. Like, somebody told me that, and I was just like, okay, sure. And then they told me RTMPS is RTMP over a TLS connection. And that's like, oh yeah, that makes sense. You open a TCP stream, do the TLS handshake, and then send some RTMP data. That makes total sense. There was also RTMPT, which was tunneled over HTTP, and then RTMPTS, which was tunneled over HTTPS. But at that stage, like, why not just use HLS? Like, if you're tunneling over HTTP anyway, you may as well just do something else. Thanks.